Volcanic lightning, also known as dirty thunderstorms, happen when the ash and steam from a volcanic explosion interact with the atmosphere to generate charged particles through friction. The positive and negatively charged particles eventually generate static electricity, making it look like the volcano's eruption comes with its thunderstorm. Even lightning bolts may appear above the volcano's plume when the static electricity is great. It's no wonder ancient civilizations associated volcanic eruptions with the wrath of the gods. For example, ancient accounts of the Mount Vesuvius eruption in Italy in 79 AD describe the eruption as having lightning blazes. Eternal Flame Falls. Found in Chestnut Ridge Park in western New York, the Eternal Flame Falls is a small waterfall with one simple attraction: a flame that never dies and has been burning for centuries. The 8-inch high flame can be found hidden in a cave just behind the waterfalls. Scientists discovered that the flame never dies because it is fueled by natural gas seeping from deep within the waterfall structure. The gas is believed to originate from the Rhine Street Shale, which is a geological formation that dates nearly 400 million years ago. The flame is visible all year long, but there are instances where it must be relit. Travelers looking to visit this site are often told to bring matches to relight the flame if it dies out. So despite its name, it isn't eternal. But still, it seems like the gas reserves responsible for feeding the flame cannot run out. Aurora Borealis. The bright and vibrant lights seen from across the sky are called the Aurora Borealis, often called the Northern Lights. This spectacle is a naturally occurring phenomenon near the Arctic Circle and involves the sun's charged particles colliding with the atmosphere's oxygen and nitrogen. These collisions charge the gases, and then gases emit different colors that cover the night sky. Green and pink are the most commonly observed colors in the Northern Lights, but in other cases, red, blue, and purple could also be seen. The colors that the Aurora Borealis emit determine how high the gases are when they collide with the solar particles. This phenomenon has captivated people for centuries, often leading to tales and myths made by ancient people who never understood the science behind the Aurora Borealis. Fire tornadoes. Fire tornadoes are uncommon and natural phenomena, seemingly mysterious yet beautifully dangerous. Also called fire whirls, fire tornadoes happen when wildfires occur. Due to the intense heat and updrafts generated by wildfires, the air in the surrounding atmosphere becomes so hot that it rises rapidly to create tornadoes that merge with the flames. The combination of the two forces of nature eventually creates fire tornadoes. They aren't any different from regular tornadoes in terms of their size and intensity. The only difference is that flames are added to the mixture, making fire tornadoes exponentially more dangerous than regular tornadoes. Their danger lies in the fact that they do not only incinerate anything in their path, but also spread fire to the surrounding areas. Penitentes. Penitentes are named after their resemblance to hooded penitents, kneeling in prayer. Still, they are rare ice formations found in icy mountain regions, such as the Andes. They look like tall, thin blades, closely packed together to form a field full of icy spikes. The reason why penitentes are formed can be attributed to the sublimation process. This happens when snow and ice immediately become gas, instead of going through the usual process of becoming water when exposed to heat. The sunlight sublimates the ice faster, producing spire-shaped spikes called penitentes. Bioluminescent shores. There are instances wherein shores tend to get illuminated with light, creating a captivating sight. Called bioluminescent shores, this seemingly supernatural wonder or phenomenon is not a product of science fiction, but is caused by microscopic organisms that emit light. In most cases, the organisms responsible for this phenomenon are bioluminescent plankton, algae, or even jellyfish. Whenever these organisms are close to the shore and are disturbed by the movement of water, or even the presence of other marine life, a chemical reaction within their cells produces and releases light that illuminates the entire shore. These organisms emit light for different purposes, including keeping predators away, communicating with one another, or even attracting prey. Pele's hair. Pele's hair is a volcanic phenomenon named after Pele, the Hawaiian goddess of volcanoes, as ancient Hawaiians believed these were strands of hair from their volcanic deity. This phenomenon takes the form of hair-like strands of glass that form after a volcanic eruption. When an erupting volcano spews molten lava into the atmosphere, it is rapidly cooled and stretched, turning into lava droplets. During the cooling process, they become thin fibers that look like hair strands, hence the name Pele's hair. Mammatus clouds. Mammatus clouds are atmospheric phenomena that often happen during or after powerful thunderstorms. These cloud formations look like pouch-shaped and bulb-shaped objects found beneath cumulonimbus clouds. The exact reasons for the formation of these clouds are yet to be completely understood, but in most cases, mammatus clouds often form just after severe atmospheric conditions, such as a thunderstorm. They are pockets of cold air resulting from sinking within the cloud. When illuminated by the sun after a thunderstorm, they give the sky a rather ominous but dramatic look. Mammatus clouds have been seen in different regions worldwide, but they still need to be more common and quite mysterious due to how difficult it is for researchers to study these clouds and their nature. Sun halos. Sometimes the sky can be graced by a halo-like ring, often called a sun or solar halos. While they seem supernatural in origin, sun halos form when the sunlight interacts with ice crystals in the atmosphere. These ice crystals, which are hexagons, refract and reflect sunlight to create a halo-like optical phenomenon. Sun halos are almost always approximately 22 degrees from the sun and have a diameter of about 44 degrees. They can also display different colors, including shades of blue and red. Areas that commonly experience sun halos are mostly cold and elevated due to ice crystals in the atmosphere surrounding such regions. Combustible lakes. Combustible lakes, also called seeping lakes, result from flammable gases escaping from the Earth's subsurface and igniting upon release into the air. This often happens in places rich in methane and other forms of volatile gases. Such regions include those that are close to geological faults. So when earthquakes and similar events happen, the gas trapped deep in the earth can exhaust and combust. When the gas seeps into areas surrounded by bodies of water, such as lakes, combustible lakes occur, turning them into scary yet awe-inspiring sights. The most popular explosive lake is the Door to Hell, found in Turkmenistan. This site is a crater where gases have been burning non-stop for over 5 decades. Combustible lakes may be visual wonders, but they are quite harmful to the environment, especially because methane is one of the most potent greenhouse gases attributed to global warming. That's why the beauty of this natural phenomenon comes with a price that can potentially affect the entire world. Waterspouts. Waterspouts are the water-based cousins of tornadoes because of how similar they are to them in terms of appearance and origin. Just like tornadoes, waterspouts look like funnel-shaped columns that rotate, but the difference is that the columns are made of water and extend from a cumulonimbus cloud all the way to a body of water, creating a connection between the two. In most cases, waterspouts are common in warmer tropical regions surrounded by bodies of water, such as oceans and lakes, but they only happen when there's enough instability in the air. There are 2 types of waterspouts. The first is the tornadic waterspout, which develops during severe thunderstorms. Meanwhile, the second is the fair weather waterspout, which can occur without a storm and over warm water. Fair weather waterspouts don't necessarily signal the coming of a storm. While waterspouts are usually shaped like columns, they can exhibit different shapes and sizes. In most cases, they are slender, but in other cases, they can be large structures resembling wedges. However, most waterspouts are relatively harmless to modern ships equipped well enough, but intense and large waterspouts can be very dangerous to marine vessels, regardless of how well prepared they may be. Morning glory clouds. The morning glory clouds are unique cloud formations that can be found above the Gulf of Carpentaria in Australia. These clouds come with long and tube-shaped formations that make them seem unnatural. The longest cloud formations stretch as far as 62 miles. Visible only between September and November, the clouds form due to high humidity and strong winds. The humidity in the surrounding atmosphere allows the clouds to form. Meanwhile, the strong winds are responsible for blowing the clouds as they form, allowing them to have a tubular shape. In most cases, the morning glory clouds are followed by thunderstorms and are indications that the weather is shifting from dry to wet. The indigenous people in the area have long been observing these clouds and have associated them with spiritual traditions, believing that the clouds are responsible for carrying the spirits of their ancestors. Snow chimneys. Snow chimneys are snow structures that look like chimneys and blow hot air through the openings at their tip. They are products of steam trying to escape through the ground in regions with extremely cold temperatures. In most cases, snow chimneys happen in volcanic regions, with ambient temperatures below freezing. Steam produced by the underground volcanic temperatures melts the ice near the surface and turns it into water vapor. As the water vapor enters the atmosphere, the freezing ambient temperatures freeze it and turn it into an ice tower. The entire chimney-like appearance is completed by the steam coming out of the hole at the top of the tower. Sailing stones. It is well known that stones are lifeless objects that cannot move on their own. However, sailing stones are rocks capable of moving through flat surfaces without anyone dragging them across the sand or mud, leaving people to wonder if something supernatural is happening. However, these stones don't move on their own. Instead, sailing stones are caused by sudden changes in the weather conditions. When there is rain just before a sudden drop in temperature, a thin layer of ice forms around the stones. Due to the slippery nature of ice, wind can easily blow and move stones through the mud, making it look like sailing stones move on their own. Even the heaviest rocks can move with a slight breeze when ice forms around these structures. Uranium. Uranium is one of the most essential elements in modern history because of its role in developing nuclear weapons and energy. Its primary isotope, or a variation of the element, is uranium-238. Uranium may be found on Earth and is expected in the planet's crust, but uranium extraction is tightly regulated due to its different effects. Because of its association with nuclear weapons, it is one of the most volatile elements on the planet, making it arguably one of the most dangerous elements. While uranium is helpful for nuclear reactors, which provide energy to different parts of the planet, radioactive waste disposal is one of the biggest environmental concerns. Disposing of nuclear waste improperly can have adverse environmental effects. Thorium. Named after the Norse god of thunder, thorium could be one of the essential elements for the future of science and technology, especially in the nuclear field. It's not the same material used for Thor's hammer. Still, this radioactive element could be a better alternative to uranium as an energy source because thorium doesn't undergo nuclear fission when an atom's nucleus or core splits into two. Instead, its isotope, thorium-232, is a fertile element that can absorb a neutron, a particle found in the nucleus of an atom, and turn into uranium-233, which can be used in nuclear reactors. Thorium's stability is why researchers believe it can be a better element for nuclear reactors. Stable elements are less likely to cause nuclear accidents, making them a contender for a more sustainable energy source that minimizes environmental concerns. However, the biggest challenge is that the methods used to extract thorium are more expensive than those used to extract uranium. The nuclear applications of thorium are also still being studied, but if thorium's practical uses are proven to be safer and better than those of other radioactive elements, it may be able to solve the world's quest for a cleaner and more reliable energy source. Potassium. Potassium has a radioactive isotope known as potassium-40, which is less radioactive than other radioactive elements, but still contributes to the natural radiation in the environment. It is an essential element for living beings and helpful for different applications. Potassium-40 is used for radiometric dating, which calculates the age of natural Earth-based materials by measuring the presence of a radioactive element. Geologists can estimate the age of rocks and fossils by measuring the ratio of potassium-40 to argon-40, another radioactive element, making this element helpful in understanding the planet's evolution. Due to its low radioactivity, potassium doesn't have the industrial applications other radioactive elements have. Still, it is one of the safest radioactive elements and has helped advance geology and other similar scientific fields. But it's not always the safest element out there. When used in the form of potassium chloride, it can be lethal and is one of the 3 drugs used for lethal injections in the US. Carbon. Carbon is the fundamental element of all organic compounds on Earth. Its radioactive isotope is carbon-14, formed in the atmosphere when exposed to space particles known as cosmic rays. Carbon-14's presence in the atmosphere allows it to be absorbed by living organisms when it is incorporated into carbon dioxide and is absorbed by plants. It's then incorporated into plant fibers through photosynthesis, the process by which plants use sunlight as their energy source. Due to its availability in organic substances, carbon-14 is also widely used in radiometric dating. Living organisms absorb carbon-14, which allows scientists to estimate the age of organic materials using the presence of this radioactive element. That's why carbon-14 is one of the most essential elements in archaeology. Carbon-14 contributes to the planet's natural radioactivity, but is a mildly radioactive element that poses little to no risk to living organisms. Because of its applications in archaeology, it has contributed to our understanding of history. Radon. Radon is a noble gas with a radioactive isotope known as radon-222, formed in the Earth's crust through the decay of uranium and thorium. As such, it is a byproduct of two highly radioactive elements, making it moderately radioactive and quite dangerous. The biggest concern about the safety risks involved with radon is that it can accumulate in homes, buildings, and other enclosed spaces. As a colorless and odorless gas, radon is undetectable to human senses. So when it reaches high concentrations in enclosed spaces, increased indoor radiation exposure can lead to diseases, such as lung cancer. It is estimated that as high as 14% of lung cancer cases in the world can be attributed to radon exposure. That is why ventilation is essential in enclosed spaces, as radon can accumulate and pose health risks. Polonium. Polonium was discovered by Marie and Pierre Curie and was named after Marie's home country, Poland. In 2006, it made headlines all over the world when it was found that a former Russian citizen named Alexander Litvinenko died due to polonium poisoning. Polonium's high radioactivity is why it can be a dangerous metal. Polonium, however, is a rare element with few industrial uses. For example, it's one of the elements used to initiate nuclear reactions. In the past, it was used to detonate the earliest versions of the nuclear bomb. Besides that, it has limited practical and noble applications, making it one of the more useless radioactive elements. Handling polonium also requires caution and special equipment due to its hazardous nature. Moreover, it is extremely dangerous when used for malicious purposes, even when it isn't used to detonate bombs. Radium. Marie Curie and Pierre Curie were responsible for discovering radium in 1898. It's an alkaline earth metal that is moderately radioactive. Radium's most common isotope is radium-226, which can decay further to produce the more stable lead-206. The decay process of radium-226 was used for early versions of glow-in-the-dark paints, as it allows radium to emit light. However, an advanced understanding of radioactive elements made it clear that exposure to radium was dangerous, especially if ingested or inhaled. That's why it is no longer used for glow-in-the-dark paints and clock dials, as it can potentially cause bone cancer due to how it bonds with bone tissues. Technetium. Technetium is the first radioactive element with no stable isotopes, which means that all of its isotopes are radioactive. Technetium-99m is the most helpful isotope of this element because it can be used for medical applications, specifically single photon emission computed tomography, or SPECT, an imaging procedure that views how blood flows through arteries and veins in the brain. Technetium-99m is used for medical purposes because of its short half-life, which is the time it takes for the element to reduce to half its original value. Elements with shorter half-lives minimize patients' radiation exposure. However, technetium's lack of stable isotopes and rarity limit its industrial applications. Its help in revolutionizing nuclear medicine is one reason this element is widely accepted in healthcare, as it minimizes potential health hazards. Promethium. Promethium is one of the 24 known elements that don't occur naturally on Earth, making it synthetic. This radioactive element has no stable isotopes, with promethium-145 being used in nuclear reactors. However, promethium has limited applications. One of the most notable applications of this element is using self-lighting signs, because the decay process that promethium undergoes allows it to produce visible light. It can also be used for atomic batteries in spacecraft because of the energy that its heat and radiation radiation produce. However, due to its high radioactivity, promethium requires strict regulations in handling and disposal. Moreover, its use should be controlled because it can lead to severe health and environmental risks when misused. Americium. Americium is a synthetic transuranic element created by bombarding plutonium with neutrons, or an uncharged particle, in a nuclear reactor. Its isotope, americium-241, is used in smoke detectors because it emits particles that allow it to trigger the alarm in smoke detectors. Despite the low supply of americium, its effectiveness in fire safety measures and minimal risk make it one of the most notable radioactive elements. Its short half-life also minimizes its dangerous and radioactive elements when exposed to humans. However, strict measures remain to dispose of americium smoke detectors. Americium has few other industrial or practical applications outside of fire safety. However, due to its high energy output, it can be used for spacecraft batteries in the future, making it an intriguing element for scientists to study. Californium. The transuranic element californium's most stable isotope, californium-252, can emit neutrons, giving it a high potential in many fields of science and technology. Californium-252 can be used in neutron radiography to obtain detailed images of materials and structures in scientific research. It can be used in medicine for cancer treatment, where tumor cells are bombarded with neutrons to force nuclear reactions. However, californium is limited, making it difficult for scientists and researchers to take advantage of its medicinal, industrial, and scientific versatility. It is also intensely radioactive, making it hazardous when mishandled. It was discovered in the University of Berkeley, thus explaining why it was named after the state of California. Tritium, hydrogen-3. Tritium is an isotope of hydrogen, also called hydrogen-3. While it may be radioactive, it has found many practical uses because of its relatively short half-life and the minimal risks involved with its use. In most cases, tritium is used for exit signs and watches because it has a self-luminous property, meaning it can produce light independently without an external power source. However, it can also be used for applications as big as nuclear weapons and reactors. When weaponized, it can boost the power of nuclear explosions. But when used as an experimental power source, it helps nuclear reactors generate more energy. Iodine-131. Iodine-131 is an isotope of iodine with an unstable nucleus, giving it its radioactive properties. While it may be radioactive, it is widely used in medicine due to its versatile properties, especially in nuclear medicine. This element can manage hyperthyroidism, a condition that occurs when the thyroid gland produces too many thyroid hormones responsible for regulating the body's metabolism and development. Due to the radiation it emits, it can also be used to treat thyroid cancer. However, iodine-131 can also be used for industrial purposes, especially in radiography or sterilizing or cleaning different materials. When used in radiography, it can detect problems in industrial materials used for buildings. Iodine-131 has versatile uses and minimal health and environmental dangers, making it one of the most valuable radioactive elements. Cesium-137. Cesium-137 is an isotope that has found purpose while acting as a dual-edged sword due to its usefulness and potential environmental risks. Regarding its industrial applications, it can be used for gauges that measure the thickness and density of different materials, such as paper and soil. But while it may be helpful, it has been detected in areas affected by nuclear testing and accidents, such as the Chernobyl disaster. Its long half-life also makes it dangerous to the health, especially in long exposures. Cesium is also so reactive that it can eat through glass. This is why careful management is necessary when using cesium-137, as it can potentially lead to health problems for industrial workers exposed to its radiation. Industries that often handle this element should also address proper disposal to avoid a similar incident to Chernobyl. Newton's first law of motion, also known as the law of inertia, states that every object will remain at rest or in uniform motion in a straight line unless compelled to change its state by the action of an external force. A bike rolling down a hill will keep moving until it hits something, unless someone hits the brakes. Every object in the universe acts like that. Whether an object is stationary or is moving on a straight path, it will remain that way until something changes that fact. But the law assumes the lack of friction and other forces, such as air resistance. Newton's first law implies that a bike rolling down a hill will never stop moving unless something stops it. That doesn't happen on Earth, even if it doesn't hit anything or if someone doesn't hit the brakes. That's because the first law law is only valid in a frictionless environment. There are microscopic irregularities in objects, and friction happens when the surfaces of two objects move against each other and cause resistance due to the irregularities. Simply stated, rougher surfaces have more irregularities and will cause more friction when rubbed against other surfaces. Meanwhile, smoother surfaces are less likely to produce lots of friction, but still have microscopic irregularities that can still produce friction. Newton's second law of motion. Newton's second law of motion in math terms is force equals the mass of an object multiplied by its acceleration, which is the rate at which the object picks up speed. That means that the force a moving object produces depends on how heavy and fast it is picking up speed. Similarly, the equation can be twisted to get the object's acceleration, which means that an object accelerates depending on how heavy it is and the force exerted on it. If you were in a grocery store with your mom and were asked to push the cart, when the cart is still empty, it doesn't take too much effort to push it forward and allow it to pick up speed. But as your mom puts more stuff in, the effort required for it to accelerate is now more significant. This explains why balls are more accessible to push than boulders. At the same time, a moving object that's heavy and picking up speed rapidly can also produce more force, which is why a runaway truck is more dangerous than a runaway sedan. But the same law also means that lighter objects can move faster than heavier objects when the same force is applied. So if you place a V6 engine inside a sedan, it will move faster than a pickup truck with the same engine as long as all of the other variables are unchanged. Newton's third law of motion. This one can best be summed up with the saying, for every action, there's an equal and opposite reaction. It sounds like karma, basically what goes around comes around, but that isn't entirely the case. According to Newton, when you move, there will always be an opposite reaction exerted by another object. The mere act of stepping on the floor already produces that reaction. A step produces a force that is exerted on the floor. Meanwhile, the floor exerts the same force back to our foot in the form of resistance, allowing you to feel that bounce in your step. If the floor doesn't produce the same reaction, you won't be able to move forward because your foot will only end up sinking. It's similar to the recoil from firing a gun. When you pull the trigger, force is created to propel the bullet forward, but the same force exerted on the bullet to propel it forward also pushes back, which causes the gun to recoil. The bizarre part is that this law applies to objects that aren't in motion. Gravity's force of attraction pulls your desk down to the floor, causing the floor to exert the same force on your table, allowing it to stay where it is. The law of universal gravitation. I promise, this is the last Newton's law. According to Newton, any particle of matter in the universe attracts any other with a force varying directly as the product of the masses and inversely as the square of the distance between them. It sounds like a mouthful, but it simply states that an object with a greater mass produces a stronger gravitational force. The law was used to observe our solar system and explain why all the planets circle the sun. The sun is the most massive object in our solar system, producing a stronger gravitational force than any other celestial body close to it. It's not as if the other planets don't produce their gravity, it's just that the sun is so massive that its gravity makes it the centerpiece of our solar system, accounting for 99% of the solar system's mass. Newton's law says that the distance between two objects also dictates the force of gravity they produce. This explains why the inner planets in our solar system are smaller than the outer planets. They have relatively low gravity and cannot attract large amounts of gas to their atmospheres. In contrast, planets like Jupiter are so giant that they produce enough gravity to pull more materials and gas toward them. Conservation of energy. The principle of conservation of energy states that energy can neither be created nor destroyed, but is only transformed from one to another. In this case, energy is a basketball that passes from one player to another. It will still always be just one ball. Its appearance might change due to dirt or wear and tear, but it's the same ball. This means that the energy in our world already exists and is never created out of thin air. We just convert energy. In the biological world, plants convert solar energy into food to survive. Animals convert the plants into food, which other animals or humans eat for energy. In this case, energy was never created, but transformed and transferred from one object to another. It can't be destroyed either, so when an animal dies, its remains go back to the earth to be used by plants for sustenance. balance. As they say, it's the circle of life and how the conservation of energy works. That was bad. So no energy is created when we create or generate energy with our power plants. They simply use energy from different sources and transform it into usable energy, electricity. For example, solar panels don't create energy from the sun, but only transform solar energy into usable energy. In this case, energy conservation is a game of give and take, where the universe keeps passing around energy that has existed for as long as the cosmos has existed. The laws of thermodynamics. First, the zeroth law says, if two things are in thermal equilibrium with a third thing, they're in equilibrium with each other. It's the ultimate mediator between two different systems with different thermal readings. It keeps the peace between two temperatures in a proverbial boxing ring. Then there's the first law of thermodynamics, based on energy conservation law. You can't create or destroy energy. This forms the foundation for understanding heat transfer and how energy is converted in different thermodynamic systems. After all, thermodynamics is the study of how heat and energy work and move within a system. The second law of thermodynamics states that some energy becomes unavailable for work when energy is transferred or transformed. This is the concept of entropy, the amount of disorder or randomness within a system. Simply stated, energy gets wasted in any process, but isn't destroyed or rendered unusable in a system. When that happens, things become more chaotic. Combined, the first and second laws of thermodynamics explain why perpetual motion machines, or machines that can move without an external energy source, are impossible. It violates the fact that energy can neither be created nor destroyed. Moreover, according to the second law, a machine will eventually lose energy to friction or heat and stop moving. Finally, the third law of thermodynamics says reaching absolute zero temperature is impossible. This is because the third law states that the entropy of a system also approaches zero as the system's temperature reaches absolute zero. As you get closer to zero, the randomness explained in the second law also decreases and goes down to zero. This violates the laws of physics because the second law states that a system will always have entropy. Maxwell's equations. Maxwell's equations are fundamental equations that describe how electric and magnetic fields behave and interact. Think of these equations as the ultimate cheat sheet that explains how electricity and magnets work. The first is Gauss's law for electricity, which describes how electric charges create invisible forces called electric fields that can push or pull other charges. Meanwhile, Gauss's law for magnetism talks about how moving electric charges or changing electric fields can produce magnetic fields, invisible areas around a magnet that can influence other objects or move charges that also have their fields. The third is Faraday's law of induction, which says that moving a magnet near a wire can make electricity flow in the wire. We make electricity in a wire simply by moving a magnet or changing a magnetic field. This is precisely how generators work. Ampere's law, with Maxwell's addition, states that an electric current in one wire can create a magnetic field that loops around it. But Maxwell added that magnetic fields can also be produced by changing electric fields, allowing us to see a bigger picture of how electric and magnetic fields interact. Ultimately, these concepts allow us to understand how electricity and magnetism work with one another and how they are interrelated in many different fields and technologies, such as communication devices, power grids, and even MRI machines. The principle of relativity. When you're in a moving bus and doing all sorts of activities with your friends, such as throwing a ball around, everything seems normal to you and everyone else on the bus. But things are a blur for someone watching you from the sidewalk, because they only see a bus moving at 80 miles per hour. They may see the ball moving, but it's moving at almost the same speed as the bus. That's the principle of relativity in action. Simply stated, the principle of relativity states that the law of physics are the same for everyone, no matter how they move. Whether you're conducting an experiment inside a train or in an office building, the results will always be the same because of this principle. It's the referee who keeps everything fair in a heavyweight physics bout. The twin paradox applies this principle. Here, one twin stays on Earth, while the other travels near the speed of light. The one on Earth ages at the same rate, while the one traveling in space ages slowly because time moves slower for objects moving fast. So by the time the space-traveling twin returns to Earth, he will be older than the one who stayed hit home. So whether you're standing still or moving at the speed of light, the principle of relativity says that you still have to follow the same rules of physics that everyone else does. No special treatment in physics exists, regardless of how fast you're going. The standard model of particle physics. The standard model of particle physics is a theory that describes how elementary particles interact through three fundamental forces: electromagnetism, the weak force, and the strong force. It's like a puzzle that tries to explain how atoms or particles work together. Or think of it as a giant Lego set, with every brick representing particles. The instruction manual that comes with the Lego set represents the standard model of particle physics. Particles are divided into two categories. The quarks are the protons and neutrons, which are at the center of the atom and make up the nucleus. Meanwhile, the leptons are the electrons, which surround the nucleus, or core of the atom. These particles interact with one another in different ways, but you can think of them as different types of forces. Electromagnetism, for example, is the attraction between magnets. Meanwhile, the strong force holds quarks together inside protons and neutrons, similar to how you might want to use glue to hold Lego bricks together. On the other hand, the weak force helps particles change types, like how you might want to swap different Lego bricks with different colors. Quantum entanglement. When two particles are entangled, there exists a seemingly magical link between them that can be difficult for physics to understand. No matter how far apart they are still connected, such that one particle feels what happens to the other particle. In simple terms, quantum entanglement is the situation wherein certain aspects of one particle in an entangled pair depend on the aspects of the other particle, regardless of how far apart they are. Another good way of looking at it is when you have a special dice and that whenever you roll it, the same number also appears on your friend's dice if they roll theirs. A mysterious connection exists that the best minds in physics can't explain. It challenges everything science knows about space and time, yet it happens naturally in our world, among atoms of living creatures, or even inanimate objects. Quantum superposition. Quantum superposition involves an object being in multiple states simultaneously, until we observe the object's actual state. It's like how all jigsaw puzzle pieces can be in multiple states because they can fit into any part of the picture, but it's only when you observe the pieces you know where they belong. The perfect example of an experiment that uses this concept is Schrodinger's cat. This experiment involves a cat placed inside a sealed box. Its fate is dependent on a dangerous particle in a superposition. The catch here is that no one knows if the particle killed the cat or if it survived. Only when someone opens the box will the cat's fate be revealed. So before opening the box, the cat is dead and alive, putting it in a superposition state. In short, anything can be true or false until we observe the world around us. Similarly, a particle in quantum superposition can exist in multiple states until it is observed. Returning to the jigsaw puzzle analogy, we only see where the pieces fit until we observe them and the bigger picture. Quantum physics tells us that everything in the world is possible until the moment of observation. Heisenberg's uncertainty principle. You're in a scenario where you're trying to catch a mosquito that has been bugging you for a while. The more you focus on its position, the less you know how fast it is. Similarly, if you focus on its speed, you won't be able to observe its exact position. Heisenberg's uncertainty principle operates in the same way. Heisenberg's uncertainty principle states that it is impossible to simultaneously and precisely know the position, speed, and direction of a quantum particle due to the limitations in measurement accuracy. This principle is like a balancing act. It's rooted in the observer effect, which states that observing an object will change its behavior. So if we measure a tortoise moving at 0.5 miles per hour, we know its momentum, but not its exact position, because it is now in a constant state of motion. But if we measure its exact location, we won't be able to get its exact speed, because we are now focused on where it is, rather than how fast it is going. The uncertainty principle is Heisenberg's way of telling us that there is no absolute certainty in pinning down particles' exact position and momentum in the quantum world, where uncertainty rules over certainty. Quantum tunneling. In the quantum world, particles can do something impossible: pass through impenetrable barriers. Classical physics says this is impossible because one particle can only occupy one space at a time. How does a particle pass through a barrier if that's the case? That's the principle of quantum tunneling. Think of it as similar to how you try to walk through a closed door, but suddenly find yourself on the other side without trying to open it. But it's not like you found a secret passage. Similarly, particles cannot access a passage that can penetrate barriers. But the quantum quantum world tells us that these particles have a unique teleportation ability to do what seems impossible. The universe says, hey, I'll give these particles the ability to sneak through walls, even though you thought they were impenetrable. But this is not because of a mystical ability. Instead, it's due to the wave-like nature of particles, which allows them to simultaneously exist on the other side of an impenetrable barrier. The catch is that quantum tunneling is less likely to happen the higher an object's mass is, making it unlikely for objects larger than a particle to pass through barriers. So you might want to forget about teleportation, because it's unlikely to happen anytime soon. Quantum computing. Regular computers are capable of two things. They can either be on or off. But let's say there's a quantum computer that has superpowers, in the sense that it can be on, off, or both on and off simultaneously. That's the basic principle behind quantum computing. In the regular world, computers exchange bits that can only be 0 or 1. However, in the quantum world, computers exchange quantum bits, or qubits, which can exist in multiple states simultaneously because of quantum superposition. So these bits can be 0, 1, or both 0 and 1 at the same time. In this case, superposition allows quantum computers to process information much faster than regular computers. They can do multiple tasks simultaneously while taking on multiple routes, allowing them to solve the most complex problems until they reach a solution. Of course, quantum computers use quantum mechanics to solve problems that even supercomputers aren't capable of. The double slit experiment. The double slit experiment can be explained in a situation where you have a small cannon that can shoot tiny marbles toward two slits, and there's a wall behind the slits. In classical physics, you're supposed to see two bands on the wall because the marbles are supposed to split and pass through the two slits. However, the double slit experiment has a different result. In this experiment, interference patterns that can only be exhibited by waves will appear in the wall behind the slits when particles are shot through double slits. But how is this possible? If you recreate the same experiment using the example we used about the marbles, you will get two bands on the wall. However, for particles, ripples will appear, as if the particles behave like waves instead of solid balls. The double slit experiment suggests that particles have a dual nature, in that they can be solid or act like waves. But the trick here is that the particles only exhibit this behavior when they are shot through slits. It's like a magician pulls off the old switcheroo within the slits and changes the particles into waves. This experiment shows that things in the quantum world don't always behave as classical physics tells them to. Particles can have a dual nature, in that they can exhibit wave-like behaviors under certain circumstances. The exact reason for this behavior is the subject of ongoing studies. This is why the double slit experiment only supports the theory, but does not prove it. Wave-particle duality. In the quantum realm, particles can showcase a dual nature. A particle behaves like a particle when observed, but when unobserved, it can display properties similar to a wave, exhibiting interference patterns. The challenging part here is that particles and waves are supposed to behave differently according to classical physics. However, in the quantum realm, particles have the dual properties of both a particle and a wave. Experiments like the double slit experiment showcase this duality, but it's not as if the baseball in your hand can suddenly turn into a wave. It's much more complex than that, and rooted in the unique and uncertain aspects of the quantum world. The uncertainty principle also plays a role here. Depending on our observation, the innate uncertainty of particles in the quantum world contributes to their dual nature, making them exhibit particle-like or wave-like properties. This ultimately means that particles, when observed in the quantum world, are versatile and can play different roles depending on the situation and how you observe them. Quantum field theory. In the quantum field theory, at every single time, there exist different types of fields that we cannot see. These fields can be magnetic fields, electric fields, or gravitational fields. All these fields have unique properties that have different effects on certain objects or particles. When these fields interact, they create scenarios where particles behave in various ways. Simply, when you toss a pebble into a pond, it creates ripples through the water. That pebble is a particle. Every particle has a quantum field, represented by the ripples created by a pebble thrown into a pond. When these particles interact with one another, the fields interact as well. So if you throw two pebbles into a pond simultaneously and close to one another, you will see their ripples either turning into a wave or canceling each other out. But instead of a pond, the quantum field theory appears more like a dance floor. When the fields generated by the particles interact, the particles particles will start to act like dancers, twirling on the dance floor, spinning, jumping, and moving around from one place to another. The quantum field theory tries to unify the movements created by all the particles interacting. It provides a framework often used in quantum mechanics and explains the quantum world and the different things happening in the most miniature observable world of atoms and particles. The observer effect. Say you wanted to take pictures with your camera after observing a particular scene. For example, you want to capture a scene of two lovers kissing, but when you look at the photo, the scene changes into two people fighting each other. This is similar to how the observer effect works. In the quantum world, observing particles can influence their actions. On the other hand, in the everyday world, observing things for what they are doesn't change their nature or what they're doing. But in quantum physics, particles are shy enough to change their behavior when they know you're observing them. It's like someone is invisible only whenever another person is looking at them. Observation is commonly supposed to be a neutral act that doesn't change the outcome of an experiment or any observable phenomena. A house will always be burning if you observe the flames turning wood into ash. In the quantum world, however, observing particles' actions can change how they act, and there's a reason why this makes sense. Picture this: you aren't observing anything in a pitch-black room that's too dark for anyone to see, but when you turn your flashlight on, the room changes from dark to semi-lit simply because you used a tool to try to observe your surroundings. You can also picture it as putting a thermometer in hot water. Because the thermometer is colder than the water in the pot, adding it to measure the water's temperature will slightly alter the water's temperature compared to what it was before. That is basically how the observer effect works. Observation can change the behavior of atoms because measuring tools can already have a huge effect on the small events happening in the quantum world, where even a speck of dust is already an entire planet larger than an atom.